Hello. In this video we're going to look at matrices as they are used in Markov chain models and looking at how eigenvalues and eigenvectors help contribute to information about those models. So let's start. A stochastic sequence is any sequence where the values are randomly determined, and a mathematical model of a stochastic sequence will be created by producing equations that govern the probabilities of where a state is, rather than the values of a sequence. So we're going to focus on a specific type of stochastic sequence called a Markov chain, named after Andrei Markov, a Russian mathematician. A Markov chain is a stochastic sequence where the probabilities associated with the future depend only on the current state rather than knowing an entire history. And sometimes Markov chains are described as memoryless processes. So for example, here's a room, and let's imagine I start in room A, and we can see that there are two doors. There's a door at B and a door into C. And let's say I flip a coin, a fair coin, and randomly choose, and if I wander into room B, the idea of being memoryless is once I'm in B, I don't remember where I came from. And so as I make my decision of where to go next, I don't take into account where I came from before. All I know is I'm in B. I have three doors. I could go to A or C or D. And so I'm going to wander through this little chamber, walking through the doors, and we're going to assume a simple model where my probability of choosing a door is based on how many doors there are. So when there are two doors leaving a room, I have a 1 in 2 chance for each door. When there are three doors in each room, then my probability of choosing any given door will be a third. Now we could do more complicated models where the different doors have different weights, but we're going to choose this simple model for now. So we're going to create a more abstract representation of our model. We have 4 rooms, and we're going to consider that as 4 vertices on a graph. And we'll create something called a directed graph where our edges are going to be from one vertex to the other with arrows. And so here's an illustration of what we might have. I've got, for the same story that we had, if I start in room A, I could choose one of 2 paths. I could either go to B or I could go to C. And so in any given state, I can leave that state by following arrows directed away from my vertex, and that'll tend me into another vertex. So notice doors. So we're going to label each edge of this graph with a number, and those numbers are going to be associated with probabilities. So from A, I have 2 paths each with probability of a half. Coming from B, I have 3 edges. Each of them are labeled with probability 1/3. C is similar to B. There are 3 edges, each labeled with probability 1/3, and D has probabilities 1/2. Now, in general, we could label any probabilities on those for a more complicated model, but we have one requirement. We require that the sum of all of the probabilities leaving J bar I is the probability of going from I to J. So if I hold I fixed and I sum over all possible ending vertices, the probability has to be 1. And that really says that the sum of all my arrows labels going away from a vertex, they have to add up to 1. That's what it takes to create something called a stochastic matrix. Well, once I have all of those labeled, we could create a matrix and store the probabilities instead of a graph. And so this matrix, P, contains the same information as our directed graph. First column corresponds to my vertex A, or state A. My second column is B, my third is C, and my fourth is D. And the rows correspond to the output vertex. And we have to follow the same order, just like whenever we do our matrix operations. So the first row will be that the vertex, or the directed edge, ends in vertex A. The second is that we end in vertex B. The third is we end in vertex C. And the fourth is we end in vertex D. We're now ready to talk about how we go from the transition matrix P that we've just calculated to understanding how we can calculate the probabilities that we're in different states at a certain time. So we're going to define our state vector. It's a vector. We use pi for probability because it sounds like P. We can't use P because that's the name of our matrix. And it has a subscript because this is actually a sequence. We have a sequence of states. And so this is a vector with 4 values, and it's at every time n, or every step n, it's keeping track of the probability that my state is in each of the 4 sites. So we have a probability we're in A, in B, in C, and in D. And this is at index n because I have a sequence. And that index is counting how many steps I've taken or how many room changes we've gone through. So if I know the state, then I want to know how would I calculate the next probability. So here we have the probability as an example, the probability that I'm now in site A at index n plus 1. And so what we're going to do is we're going to add over all of the incoming directed edges, so all the arrows coming and pointing into site A, we'll calculate this sum. And so notice every term has this basic form. We have the probability of a site at the previous step, and then we'll have the transition probability from our matrix. This PA to A is actually 0, so that would be a 0 in this value. But if we could also say, all right, well, maybe I came from B. So I have the probability I was in B, and then I multiply that by the transition probability of if I'm in B, what's the probability I go to A, and remember that that was 1/3. So I do that for each of the 3 sites, or 4 sites. So I have probability coming from A, coming from B, coming from C, and coming from D. And so I get this nice linear combination. Now because this is a linear combination, we can think of that as a matrix vector multiplication. And again, we have an iteration with matrix multiplication. The probabilities at index n plus 1, we get that by taking the probabilities at index n and multiplying on the left by our transition matrix P. Now, say we go back to the very beginning, we say, all right, what's the probability of my state at time 0? Completely determined. So for example, if I start in site A, then this initial distribution, I have 100% of my probability I'm in A and 0 for the other 3. Or I could say, I don't know where I am. I maybe have probability of 1/4 in each site. Regardless, we have some initial distribution. I can now calculate the probability distribution for index 1 by taking our initial distribution and multiply it by P. If I want to find the distribution at time 2, I take what I just calculated for pi 1, multiply that by P, and I could repeat this on and on and on. The thing is, my pi 1 is actually calculated as a matrix multiplication, so I have P times pi 0, so we actually end up with P squared. Well, what's happening is each time I iterate through my index, I have 1 extra power of P. So if I want to know what's the probability at index 3, I take my initial distribution and I multiply it by P cubed. And in general, if I want to know what's my distribution after n steps, I take my initial distribution and I'll be multiplying it by the matrix P to the nth power. So this gives us an interesting interpretation. The powers of my transition matrix calculate the probability distributions for multiple steps into the future. So if I start with my P matrix and I square that, I get a new matrix. And so these columns actually give me my probability distributions starting in each site. So the first column, remember, that's I start in site A. And so this first column is telling me after 2 steps, 1/3 of the time I'll be in A, 1/6 of the time I'll be in B, 1/6 of the time I'll be in C, and 1/3 of the time I'll be in D. And so I can calculate each of those values. If I multiply by P again, I get P cubed, And now, for example, this third column, which corresponds to site C, says if I start in site C, then after 3 steps, 7 out of 27 times I'll be in site A, B, or D. Now that we have this idea that we can look at powers of my matrix to understand my probability distribution, let's go back to the idea of eigenvalues and eigenvectors. So I'm going to take my transition matrix P and calculate the characteristic polynomial. So just a reminder, this polynomial comes from taking the determinant of lambda times the identity matrix minus my transition matrix. And that determinant I've calculated and simplified here. And it factors really nicely. So I get lambda times lambda minus 1 times lambda plus a third times lambda plus 2/3. And I can calculate that there are 4 eigenvalues: lambda equals 0, 1, negative a third, and negative 2/3. And to save time, I've gone ahead and calculated a basis vector for each of the eigenspaces. So the eigenvector for eigenvalue 0 is this vector negative 1, 0, 0, 1. An eigenvector for lambda equals 1 is the second vector 1, 3 halves, 3 halves, 1. And I have eigenvectors for my other 2 eigenvalues as well. So if I go back to my initial distribution, my starting probability distribution, I have 4 linearly independent vectors in R4. And so those 4 vectors form a basis for R4. I can write my initial distribution as a linear combination of those 4 vectors. Now I don't necessarily know what those C1, C2, C3, and C4 are yet, but I know I can do that. And after n steps, I can think of that p to the n power being multiplied by this linear combination we've calculated. When I distribute my power of the matrix to each of those 4 vectors, then it has the effect of multiplying the vector by the eigenvalue n times. So because V1 had eigenvalue 0, that first term gets C1 times 0 to the n times the first eigenvector. My second eigenvalue is 1, and so multiplying V2 by p to the n is the same as multiplying by 1. Similarly, multiplying V3 by my matrix n times, it's equivalent to multiplying by negative a third n times. And vector 4 is equivalent to multiplying by negative 2/3 to the n. So this first term is going to go away, because that's 0. My second term simplifies to just C2V2, and so I can think of my my probability distribution after n steps as only having 3 contributions. Now I want to point out, because negative a third and negative 2/3 are both values with size less than 1, as I raise that to a power, that decays geometrically. And so these other 2 terms, they converge to 0 as n goes to infinity. What that's telling me is my probability distribution is actually converging to C2V2. I just want to figure out what that C2 is. To calculate my coefficient for my linear combination, what we're going to do is we'll set up the equation, and if we think of that as a linear combination, this is equivalent to a matrix equation where I've got my P matrix. Sorry, not my P matrix. This is the matrix formed by my eigenvectors. So the first column is the first eigenvector, and the second column is the second, and so on. So the linear combination of my eigenvectors is equal to my initial distribution. I want to solve for the vector of C's, and I can do that with the inverse matrix. So I go and calculate the inverse matrix, and my coefficients are the inverse matrix of the eigenvectors times my initial distribution. And recall, the one that we were focused on is C2. And so C2 is going to be the linear combination of the values of pi 0 times 1/5. That means that C2 is actually the sum of the distributions for times 0 over those 4 values divided by 5. Now, because the initial distribution is actually a probability distribution, those values add up to 1, and I now know that C2 is equal to, and I get a distribution. This is my limiting distribution, and in this particular case, it's called an equilibrium distribution. The reason that vector is called an equilibrium distribution is if I consider raising my matrix to higher and higher powers, notice that the values in every column are getting closer and closer to my equilibrium distribution. After only 20 power 20, I'm within 1/10,000th of it in each value in the matrix. So this is really interesting about Markov chains, but this is a good introduction to the ideas and illustrates how eigenvectors and eigenvalues can help us understand some of the properties of a Markov chain.